Derivatives of trig functions, we're going to look at sine and cosine. I already showed you the graph of cosine earlier. I'm also going to show you the graph of cosine. So if I draw the graph of cosine and I put a dot somewhere on cosine and draw the tangent, can you see right at this point we have a maximum that tangent line would be horizontal and the slope of a horizontal line is 0. And as I go along and drag my tangent line, it goes negative first all the way until it gets to pi where it flattens out at 0 again. Then my slopes become positive, flattens out at 0 again. And this pattern continues over and over again. After doing this and looking at the resulting graph of plotting all those points, we go, hey, that looks like a graph that I know. It looks like the same kind of graph, either a graph that's been translated to the left, or you might notice that this is the same as a sine graph being flipped over the x-axis. So how do we write that? Well, a sine graph being flipped over the x-axis, that's negative sine of x. So if we have cos of x, then the derivative is negative sine of x. And we saw this graph, I showed it to you earlier. If you have sine of x and you graph the derivative, well, that one works out perfectly to be just the regular graph of cos of x. Now, one of the things when memorizing these that gets tricky is that one's positive, one's negative, and you have to remember which one goes with which. It's pretty easy to see sine goes with cos, because the derivative of sine is cos, and the derivative of cos is negative sine, but how do you remember which one the negative goes with? And I actually think about the graphs of sine and cos to help me. So if I go back to my sine graph to start with. Oops, that's not where I wanted to go. There we go, get rid of that. If I'm thinking about what happens first as I drag my tangents along sine, this helps me realize it. Are my tangents positive or negative? The first part around 0, my tangents are all positive. That helps me remember that the derivative of sine is positive cos. If I think about my cos graph, so if I go back to my cos graph, start it again. If I go to the right away, what happens to my tangents? They go negative right away. So because my tangents go negative right away, that helps me remember that my derivative of cos is negative sine. So thinking about the graphs and what's actually happening with those tangents can be a way for you to remember the derivative of sine is positive cos, and the derivative of cos is negative sine. So now we can apply all of the other rules we've already learned to sine and cos as well. Now when you have f of x equals sine to the 4th x, you may actually want to rewrite this. Mathematicians don't like brackets. That's why they put the 4 where they did, but this means the same thing. If you wanted to type in sine to the 4th x into your graphing calculator, you'd have to add those extra brackets. And when you add those extra brackets, can you see the chain rule? Can you see that there's a sine x inside of the power of 4? And so how do we do our chain rule? We do the derivative of our outside function, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside. Is the derivative of sine positive cos or negative cos? Positive cos. And then if you would like, you could rewrite this with the cubed in between the n and the x again. And if you're really fine with just going from here to here, that's all right. But sometimes that 3 there makes you not realize that the sign is inside of the power of 4. It's easier when you put the brackets there to really see that sine is inside that power of 4. With the introduction of the trig functions, the chain rule can happen in different ways than we had before. When we just had powers, our chain rule was always when we had a function inside of a power. But now we could have functions inside of cos. Can you see that the 3x squared, 3x cubed, is inside of cos? And so now when we do the chain rule, we have to decide which derivative are we going to do first and what are we going to keep the same. We always keep the inside function the same. So the 3x cubed is going to stay the same. The outside function is cos. What's the derivative of cos? Sine, and it's going to be negative, so you'll get negative 4 sine. Keep the inside the same. Multiply by the derivative of the inside function. And in your textbook, they would probably simplify this. They like to put the numbers together. So negative 36, they would put this first and that at the end. I would like you to try this one. Okay, let's see how you did. This is implicit differentiation, so what we have to do is we have to take the derivative of the whole thing. So I'll just show that by writing the whole thing out, and then looking at this, when we do the derivative of the left-hand side, what's the derivative of sine? The derivative of sine, oops, I can't write dy dx. The derivative of sine would be cos y. And whenever you have a y in a function with implicit differentiation, use the chain rule and say the derivative of my inside function is dy dx equals, on the left-hand side, we have the product rule, so we keep one the same, multiply by the derivative of the other one, plus keep the other one the same, derivative of the first one, we want to solve for dy dx. So in the end, we just need to divide both sides by cos y, so we'll get 3x to the 7 times a negative sine x plus cos x times 21x to the 6. So again, introducing sine and cos, we have our derivatives, and we now can apply all the rules we've had up till now. Yes?
So like, for the y, because we can, like, in the equation, we can solve for y just by sine to the minus 1.
Right. But do we know how to do the derivative of sine to the minus 1 yet?
But
No.
we plug in the y equals 4 cosine of y and just kind of create new term signs.
We can, like, so what Ethan's saying is I can get y by itself by doing the sine inverse of both sides. And then if I knew how to do the derivative of sine inverse, then I could do this directly. But so far, that's a function we don't know. What are the functions we know so far? We know our regular ones. Have we learned the derivative of e to the x yet? No. Natural log of x? No. We just learned sine and cos, right? But we don't know. Every function has its own derivative. And so we learn them slowly. But right now, we're limited to powers, sine, and cos. We're going to add tan by the end of the day. Yes?
But because we have like a y equals, can we like substitute y for that?
Yes, you could substitute y in for that here, and then you'd have cos of sine inverse.
Yeah.
Yes. And then you'd have a function only in terms of x, yes. And you could graph that and see what that looks like. Do you want to graph this? Do you want to see what this equation looks like? I do. Sorry. If f of x equals sine x cos x, show that the derivative is cos 2x. Well, we can start by doing our derivative like normal. Can you see that there's two functions here with x with a product in between? So we would have a product rule. Product rule says keep one the same, do the derivative of the second one. The derivative of cos, is negative sine, plus keep the other one the same, and the derivative of sine is cos. So we're going to get negative sine squared x plus cos squared x. And then from grade 12, we have to remember our identities. So they're also up on the board here for you to cheat temporarily. Cos squared minus sine squared is one of our double angle identities. So here, I could rewrite this to be cos squared x minus sine squared x. And so using my identity, that becomes cos 2x. So hopefully you mostly memorized your identities last year so that you can see them and go, hey, wait a minute, that's one of my identities. And then you can apply it to a question like this, right? The next thing you could do in a question like this, right? You could get up to here, no problem. And you see that this question says, show that it's equal to this. Well, at this moment, if you just wrote from here to here, the marker, me, wouldn't know if you didn't know it, or you just wrote it down because you didn't remember, and then you would get it right that way as well. So in this case, it kind of is self-fulfilling. That's a little bit dangerous sometimes if you don't show any work, right? Some of you might have done that in identities last year. Been like, I don't know how to make this work, so I'll just write the right answer on the left-hand side and hope that it works out. Anybody use that strategy? Maybe? You know people that use that strategy and they're not in calculus? Okay. Okay, I'll get you to try this one. And the next one. Were you able to see that it was a chain rule? And that the 4x cubed plus 1 was inside cos. So when we're doing the chain rule, we do the derivative of the outside function first. Derivative of cos is negative sine. Keep the inside the same. Then multiply by the derivative of the inside. Done. Well, it's a chain rule because there is this function here is inside cos. It's not a product rule, because the number one thing, how many people went product rule on this one? Yes? So if you think there's a product rule, there has to be a product between two functions, in which case, if this was a product rule, this question would have to look like this. Notice the difference? There's that extra x. That makes this one function, this another function. But right now, if you meant this to be a product rule, this is your first function. There's no x. Cos by itself actually isn't anything, because it needs a variable there. So now we have to be able to recognize that instead, we have the 4x cubed plus 1 is inside of cos. And if we have one function inside of another function, then this is going to be a chain rule and not a product rule. And if you're doing the chain rule, the derivative of your outside function is cos. We do the derivative of cos first. Derivative of cos is negative sine. We keep the inside function the same, and then multiply by the derivative of the inside function. Have you done this one already, or do you need some more time? All right, we'll check how we did. So finding the gradient function, that's finding the derivative. We have a quotient rule here. Quotient rule says keep the bottom function the same. And I'm going to change that 1 over the square root of x to an x to the negative a half. Are you okay with that? Then multiply by the derivative of your function on top. Your derivative of your function on top is going to be a chain rule because there's a 3x inside of cos. The derivative of cos is negative sine. Keep the inside the same. Multiply by the derivative of the inside, 3. I am already there we go, moving things over so I don't run out of room. Minus, now we keep the top function the same, cos of 3x, multiplied by the derivative of our bottom function. It's a chain rule again. The derivative of sine is cos, multiplied by the derivative of the inside. Man, I still ran out of room. Negative 1/2 x to the negative 3/2. All over the bottom squared. Now I wrote squared around the whole thing. If you wanted to put that squared in between the sine and the 1 over root x, that would be fine. And we're not going to simplify this. We're just going to say we're done. Of course, in your textbook, they'll have the simplified answer. And every single time, I'm going to get you to try to do the algebra to change it. I would rather you do 3 questions and every single time do the algebra to change it, rather than doing 20 questions and never doing the algebra. Yes? Write this bigger? Okay. So we have minus. We kept the top function the same, cos 3x, multiplied by the derivative of your bottom function, which is a chain rule. First we do cos of x to the negative 1/2. Then we do the derivative of the inside function You see that better? Still too small?
Can you just add on the bottom?
This, that part alone is that. Can you see the rest? Okay. Now, when I told you about when I fell teaching calculus, because they get so long, I'm restricted for safety reasons to the smartboard now, so that I can't keep going far to the left and fall again. Okay, check out tan. Here's our graph of tan. And if I take my points and I drag them along, can you see that the tangent is always positive? And then all of a sudden you'll hop over to this one, but the tangent's still always positive. So we get a graph that looks like a bunch of parabolas. That graph in reality is your secant graph squared. Do you remember what your secant graph looks like? Do you remember how to draw your secant graph? We'll do a quick review. If you draw your cosine graph, 0 to 2 pi divided into 4 equal sections from 1 to -1. Your cosine graph starts at a maximum, then to the middle, minimum, middle, maximum. Here's your cosine graph. Wherever your cosine graph had x-intercepts, you had asymptotes. And the reciprocal, while 1 over -1 stays the same, 1 over 1 stays the same. And this was your cos graph in purple. Okay? I mean, that's not your cos graph. That's your secant graph in purple. Your cos graph in green, your secant graph in purple. If you square your secant graph, does it make sense that everything becomes positive? Squaring your secant graph, these ones just become a little bit steeper. This one becomes positive. And it just so happens when we draw all the points of a tangent graph, all the different slopes, it ends up being the secant graph squared. Now, just take a moment just to take this in. What are we doing? When I'm dragging a point along here, which I've now since lost, because I stopped it in a place where I can't find that point again. But anyways, when I drag the point, all I'm doing is plotting all the different slopes as I drag them. It could be anything. It could have been something random that we have no idea whatsoever. But it's kind of beautiful that it works out to be something that is connected to other trig functions that we know. Now, why is it that if we started with tan of x, that our derivative is secant squared? Some of you are just going to memorize that. That's fine. But if you forget, and I asked you, can you find the derivative of tan? Well, no, unless I tell you now it's secant squared. But if I didn't tell you it was secant squared, because that's what this question is, it's saying, find out that it's secant squared. Well, what could you do with tan? What's another way I could write tan? Sine over cos. And then if it's sine over cos, I could find the derivative of that. Can you see that that's a quotient rule? And you know the derivative of sine, you know the derivative of cos. Okay, let's see what happens. dy dx. Quotient rule says keep the bottom the same. Do the derivative of the top. Derivative of sine is cos. Minus keep the top the same. The derivative of the bottom is negative sine all over the bottom squared. Is that obvious that that's secant squared? Not yet. It's close. Well, what do we have on the top? Can you see if I simplify the top, I get cos squared x plus sine squared x all over cos squared x? And you recognize what the top can do? What's sine squared plus cos squared? If the angle's the same? Sine squared plus cos squared is 1. And so if I get 1 over cos squared, well, 1 over cos squared is the same thing as secant squared. So now, well, I have it in a box 2 slides later, that the derivative of tangent is secant squared. So when you have tangent and you have to do the derivative, you can go directly to secant squared. You don't have to deduce it like we just did. But if you forget it, you can always find it out. I find this is much more helpful for the other trig functions that we're going to learn in a little bit. I'll just give you a sneak preview. Choo, 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 choo. Wow, there they are. These ones, I find that, myself included, are easy to forget if you're trying to memorize them, because you don't use them very often. The derivative of cosecant, the derivative of secant, the derivative of cotangent. But it's not hard to figure out the derivative of 1 over sine. It's not hard to find the derivative of 1 over cos. And it's not hard to use the quotient rule and to find the derivative of cos over sine. These are just simplified versions of that. So you can either, with these ones, memorize them or deduce them. Okay, but that's sneak preview. We're not there yet. We are on this slide right here. Not this one, not this one, not this one, not this one, this one. Someone's done the derivative already, and they got negative sine x minus 2x. What function did they have originally? What would give you a derivative of negative sine? Negative cos or positive cos? Positive cos. What would give you a derivative of negative 2x? Negative x squared. And that would be your right answer. Plus, you could have, just says find a function, right? You could have left it like this because this is a function with that derivative. If you have a favorite number, Alvin, what's your favorite number? 8. You could take the opportunity to add 8 because it's still okay, right? If you feel like I really want to have my favorite number in there, you can do that. But it doesn't need to have add 8, right? If your favorite number is something else. It's important, though, to have a favorite number. You can't go through life without having a favorite number. And it's okay if they change. Mine have changed over time. Grade 6, my favorite number was 3. Another one to work backwards, negative 3 cos x plus 5. And so if we had a derivative of cos, would this be positive sine or negative sine to get a derivative of negative cos? Since the derivative of sine is positive cos, The derivative of negative sine would be negative cos. And then plus 5 would be plus 5x. And then you could leave it like this, or if you wanted to, add whatever number you like. Plus 8. Okay, now there's going to be people going, oh, do I always have to add 8? No, that number, this is totally optional. Optional / personal preference. Right? If you really hate the number 8, you don't have to write that number down. And for us later, we're going to find out that later on when we do these, we go plus c and say c can be any number. So we're not discriminating against any numbers, because that would be bad. And there's our derivative of tan. And maybe we'll stop there for today.